Good morning, Ben Cohen. Today we're going to talk about Riemann sums. So with derivatives, the big idea was we looked at slope, and from slope we were able to basically derive all the rules for derivatives. With integration, it's a similar concept, but instead of looking for a slope, you're looking at area under the curve. So the idea then is start with a axis coordinate plane, like so. Oh, there's one line. There's another. And if we look at, let's say, the speed. So we have the speed of a car or someone walking or something of that nature. Copy, paste. Make this one flat. There we go. I am good with this. Yep. So let's say we have some speed here. So this will be I'll say v for velocity. Though velocity is a magnitude and direction, this will just be in one dimension. And this will be with respect to time. So this will be measured in seconds, and this will be measured in meters per second. And this will be, let's say, y equals x. This will be 1, 2. This will be 1, 2. 1, 2, and so it's obvious that this is 1 over x, and then it kind of flattens out. Well, we knew how to do the derivative of this. So if we were going to look at the derivative of this, which is the slope, we would have something like rise over run, so delta y, delta x, and we would have a constant slope here of 1, and then we'd go down to 0. So the derivative would look something kind of like this. And then we'd still be measuring derivative with respect to time, but since we're looking at slope, rise over run, we would be meters per second over second. Meters per second over second, which is meters per second squared, also known as acceleration. So if we take the derivative of velocity, or speed, with respect to time, then we get acceleration. But then the question is, how do we go backwards? Or how do we go from velocity to position? And intuitively, you kind of know how to do that. For example, if you're going 60 miles per hour for 1 hour, then you know that you'll be 60 miles away after 1 hour. And totally true. And the way you did that mentally is you did a Riemann sum. You found the area under the curve. Another way that we looked at how to do that was through the linear approximation, or Euler's method. Euler's method, we had a derivative, and we took that derivative and we turned that derivative into a function. So I'm going to draw this up right now. So this will be, let's see, 1, 2, 1, 2. Now this is y equals x. We'll have 1 over x squared. Nope, I can make it a little bit less. There we go. 1 over x squared. And then from there, it will be a straight line linear. And intuitively, specifically, this will be y equals 2x. And we can look at this and verify that we're correct. Now, we'll learn how I did that later. But for now, we can look at this and see this makes sense, because this is the derivative of velocity, which will be position. So if we look at this, and this will be position in meters. Nope. That'll be time in seconds, and this will be position in meters. If we look at this right here, this function, 1/2 x squared, and we take the derivative of it, which we know how to do, because it'll just be the power rule, be 2 over 2 times x will just be x. And look at y equals 2x, take the derivative of y equals 2x, we hit 2, and we get 2 over here. So we can tell that it's correct, but intuitively we don't really feel it really at this point. Well, what happens here is you can also look at this as the area under the curve. So we have a shape here, and we could say that this shape here was created by finding the area under this point. So we want to find this height right here. That would just be at 2. We just find all the area under this triangle up to that point. Now, to make it feel correct, give the right sense of intuition here, we'll look at it from a point of dimensions of units. So the units for this then, if we're trying to find the area under this curve, well, the area is a length times a width. So this is a triangle, so we would find, this would be the seconds, so we'd have 2 seconds on this side, and then this vertical is meters per second, and it'll be 2 meters per second. And so when we multiply those together, we'll get 4 meters per second times second. Seconds cancel, and we get 4 meters, which is a position. So if we look over here, we have distance here, we have position here. And so it kind of makes sense then from a dimension point of view that when we take the area under the curve, we can get the antiderivative or the integral, so to speak. So let me lay this out then in a more linear fashion. So we had 3 graphs that we created. We started with, so we have one that looks kind of like this, which is 1 over x squared, and then goes linear. We had one that looks like this, which was velocity. This is distance. These are all measured in time. And then we had an acceleration, which looked something kind of like this, time, and then acceleration. So what I said was we started off with f of x like this and showed that we already know how to find f prime of x over here. But then we can also find something using the area under the curve that I'm going to write as big F of x. And that's referred to as the integral of f of x. It'd be just as legitimate to say that, no, this, I'm going to call this g of x, and then this is g prime of x, and this is g double prime of x. So the point that I'm really trying to get here is if you want to go to the right, like this, you take the derivative, or the slope of the curve. If you want to go to the left, then you're going to find the area under the curve, or take what we call as the integral. And look at the units here. This will be measured in meters, this will be meters per second, and this will be meters per second squared. So that's the idea of what we have for integrals and derivatives. The other way of looking, there's really 2 ways of looking at integrals. One is this intuitive, semi-intuitive, area under the curve method. The other way is just from a pure mathematical point of view. Integrals are also referred to as antiderivatives. And antiderivatives is just you take a derivative and it's kind of like playing a movie backwards. Whatever rule you have for the derivative, you reverse the rule, and that's now your antiderivative. And so when we have an integral, this is an integral sign with respect to x, and you have a derivative with respect to x, f of x, this will give you back the antiderivative, and the derivative will cancel out to give you your function back. There's also going to be a constant, which we'll talk about later. And that is the idea behind area under the curve and the kind of concept of integrals and why integrals work. The key point to think of is when you're doing area under the curve, you multiply the axes by each other, and that will give you the units of your area. Okay. Step back. So the idea of a Riemann sum is just a way of finding area under the curve. A Riemann sum, put that in place. There we go. A Riemann sum is just basically a whole bunch of boxes that you use to find the area under the curve. So if you have a curve that looks something kind of like this, a Riemann sum would then be calculating these areas of these boxes to approximate the area under the curve. And if you remember from when we talked about derivatives, it's the same idea of how we found the slope of a curve. We took 2 points and found the slope between the 2 points, and as the 2 points got closer to each other, you got a better and better approximation of that slope. Same thing with a Riemann sum. If you fill a curve with a whole bunch of boxes, then you can use the area of those boxes to approximate the area under the curve. Now, it's not going to be perfect, but if you get smaller and smaller boxes, then it gets better and better approximation. This is the same thing you were doing earlier with Euler's method, where you had x and y initial, you're given some dy dx slope, and then you calculated the change in x, change in y. But the idea with the Euler approximation is you start with a derivative, and you take that derivative and you draw a curve. Now with the Riemann sum is we start with a curve, and then we find the area under the curve. Now this is all just a different point of sense of perspective. The key takeaway here is when you think of derivative, think of slope. And we think of integrals, think of area under the curve. Integrals, area under the curve. And the area under the curve is most often calculated calculated through finite means using a Riemann sum, small boxes. Now your thought might be, well, how do we draw these boxes? The long answer is however you want, but there are a couple of standard techniques. So if you have a curve like so, then you can choose your box points to be on the right and make them bigger like this, like so, or you can choose them to be on the left of the curve where they touch the curve, or you can make them look like trapezoids if you want, or anything like such. And the concept is, as long as they get small enough, it doesn't really matter how you do it, because the errors associated about where you choose the point will kind of fall away. Okay, so this is the concept of Riemann sums. And I know a lot of information kind of thrown out there, kind of jumbled, kind of theoretical. We're going to do a few Riemann sum problems, and that'll kind of smooth over some of the concept of what we're going for here. So one problem we could see would be something like this. So we're given the graph. The graph of f is shown above, for 0 less than or equal to x less than or equal to 4. What is the value from 0 to 4 integral f of x dx? And so when you see integral f of x dx, even though we haven't formally addressed it yet, this is the area under the curve. So what this is asking is, what is the area under the curve from 0 to 4? And so we look at this in terms of geometric shapes, so 0 to 4. And we break down the shapes into, geometric shapes so we can find the area. Now you could think of this as Riemann sums as a whole bunch of small rectangles. And that's traditionally how you do Riemann sums. But it's easier for us to look at these as just shapes. So this is 2, this is 1. 1 times 2 is 2. This is 2 wide. This is 4 high. So 2 times 4 is 8. 8 divided by 4, or 8 divided by 2 is 4. So we have 2 and 4. We have this side here is 1, 2, 3 long. And this is 2 wide. So this area will be 6. And so the total area of this will be 2 plus 4, which is 6. And then since this is below the curve, we'd subtract 6. So the total area, and we think of it as signed area because we're taking account negatives. So the integral from 0 to 4 f of x dx would then just be 0. Some of the points to think of for this problem is later we'll learn that how to actually make integrals based on the equations. So we could write a equation for a line here, and we could write another equation for the line here and solve those. But there's no real reason to, because again, this is just represented by area in the curve. Another point that's interesting is there's the point up here, but there's no point down here. And it's like, well, which side do you count that on? Do you count that as a positive or count that as a negative? Well, if you look at this one point in particular, you can look at it in terms of a rectangle or Riemann sum, where the height of that point is 5, but we're multiplying by the width, which is, you can call it delta x or h, which since it's 1 point, it's going to be infinitely thin. You can think of it as 1 over infinity width. And since that's going to be so small, that height from that 1 point, or any set number, a finite number of points, is negligible. So that 1 point doesn't matter if it's at the top or the bottom. It won't affect the total area of the integral. And so that's how you do that problem. So here's another problem, an actual more formal Riemann sum type problem. A tank contains 50 liters of oil at time t equals 4. So t equals 4 initially equals 50 liters. Oil is being pumped into the tank at a rate of RT, okay? Where R of t is measured in liters per hour, and t is measured in hours. Selected values of R of t are given in the table below. I'm assuming that R stands for rate. Using a Riemann sum with 3 subintervals and data from the table, what is the approximation of the number of liters of oil that are in the tank at t equals 15 hours? So I'm going to draw this up real quick. So we have some sort of graph like this. I can do that second line better. There we go. That's a little bit better. And what we'll have then is t on this side measured in hours, and we will have liters per hour, which is our rate, up here. And so we have 4, 7, 12, and 15 here. And we have 6.5, a little bit less, and finally at 5.6. And so I drew them kind of in a straight line. I don't think they're actually supposed to be in a straight line, but that's okay. And also, the biggest difference here is between 7 and 12, and that looks like I drew it as the smallest, not drawn to scale. So what they're asking for then is we're going to find the total number of liters of oil that are in a tank at 15 hours. So what we're going to do then is find the area under the curve. And you can think of this as liters per hour times hours, 15 hours, and that will give us liters. So intuitively, from a dimensional point of view, that makes sense, that we're finding area under the curve. This kind of concept is crazy useful for physics. If you do engineering or first or second semester of physics, you can pass pretty much first semester of physics just by this concept of making your units and dimensions match up. I don't recommend it, but you could. So we want to use a right Riemann sum, which means we want our rectangles to touch the right side of the curve. And so what we're going to do then is when we draw these out, 3 subintervals above table, using a right Riemann sum with 3 subintervals. So we're given that at this point here, we have 50 liters. And so 3 subintervals will be 3 rectangles. So 1, 2, 3. And the idea here was we're using the right Riemann sum, which means the right corner of our rectangle will touch the curve, like this. And so now then we find the area under the curve, light blue. And to do that then, so we'll find this will be, I'm going to write down the widths real quick. So this width will be 3, this width will be 5, this width will be 3. Normally Riemann sums all have the same width, but not always. Having the same width is nice because then you can factor out the width. So we have so we'll look at our second dot here, because this is where our height is going to be. So we'll use this dot, and that dot This will be 6.2, 5.9, and 5.6. And so the amount of oil that's going to be added in here will be 6.2 times 3 plus 5.9 times 5 plus 5.6 times 3. Now, they also gave us the point of data that we started off with 50 liters of oil. What we're calculating here is just the change in oil, so we're going to have to add in our initial condition of 50. So bring out our calculator. We'll do on clear 6.2 times 3 plus 5. Nope, that's a 2. 5.9 times 5 plus 5.6 times 3. And I'll start with this answer. This is 64.9. And then we add 50 to that. I just kind of want to see they have 64.9 up here. They do. So that's a clever wrong answer there. So we want to add 50 to this. So that's 114.9, which is also a possible answer, which is the correct answer. So to backtrack and look at what happened here, so we were told to find a right Riemann sum with 3 subintervals. So 3 subintervals is the number of rectangles that we're going to have. The width of each rectangle was based on the difference between the x value here, or the t, ours. And then the height was based on the right value, because they told us a right Riemann sum. If they told us the left, then we would have drawn the rectangles using the left point, which would have given us actually bigger rectangles, which would have given us more oil. And that's the idea, is this is an approximation, so neither of them are correct. You could be like, well, then we'll just take the average of the two. Yeah, there's lots of ways to do it. Or you can just get smaller rectangles. Either way, part of the problem they gave us, so we used the right, and so we found out how much oil was added, but then we had to add in this initial condition of 50 liters of oil. And so that's how we estimated the amount of oil in the tank at 15 hours. We'll find out later that this 50 liters here, that's the C that we'll do when we take integrals. So that is how we do one Riemann sum problem. There's one more I'd like to look at. So this question is asking what is the average value of square root of cosine of x on the interval of 0 to x to pi over 2. Draw a quick graph of that. Cosine of 0 is 1. Cosine of pi over 2 is 0. And there's a square root, so it's probably something kind of like this. We want to find the area under the curve. So this would be a calculator problem. One of the giveaways is that you have 3 digits on your answers, which means it's going to be probably not exact, which means you're going to want to use a calculator. So you probably have about 3 minutes to do this problem. So the way I would do this problem would be something like, go back real quick. So this is pi over 2, this is 0. The average value, the way you find it, is you have this area here, and you basically squish it into a rectangle so that it would look like this. And then your average value would be right there. The way you find the average value is 1 over b minus a, integral a to b, f of x dx. So long story short, this is area under the curve, and this is the width, which would be pi over 2. So what we're going to do is we're going to find the area divided by pi over 2. So to our calculator, clear, and we'll do y equals, let's see, where's the square root? Square root, cosine of x, parentheses, we'll do window, we'll go from 0 to, let's say, pi, 3.1415, and it's not going to get higher than 1, so I'll just say 2, and then we can graph this. So I'll go halfway then. 3.14 0.5, so just down to the 0. I chose the full pi as the x value. That way it'd be easier to trace. So we'll do a calculate. And if you see down here at 7, this is the integral of f of x dx. So this is going to find the integral along the curve. And so what we're really doing is finding the area under the curve. So I'm going to start by taking the lower limit. I'm probably going to do a little bit more just so I don't risk going off this. No, I'll go with that. So there, and then I'll probably make sure my y value, I'm going for 0, but just maybe a little bit above 0. We don't have to be that exact. So there we go. So I'll go back right there. That's what I want, because you can't take the square root of a negative value. So right here, and I click enter, and what's going to happen is you'll see it makes little bars. That's how the calculator is calculating the area, which is basically the same as Riemann sums. So you see here, click, 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 Riemann sums all the way through, and that's how the calculator is approximating it. It's not giving us a real answer per se. It's giving us an approximation, which is 1.198. So we have 1.198, which is interesting because we can see that it's an answer right there. So that is the area under the curve. But we're not asked for the area under the curve, we're asked for the average value, which means we have to do this divide by pi over 2. So I'm going to take 1.198, multiply by 2, divide by pi, because that's the way you divide by a fraction. Just multiply by the reciprocal. And so we go back to our calculator. We do 1.198 times 2 divided by 3.1415. And that gives us 0.763. 0.763, which is another answer right here. And so what I did with this one then, so to backtrack and kind of look at what we did, so this asks us for an average value. An average value is the average area under the curve. And so another way to think of this is, so I basically said that we take the area and we squish it into a square. So if we think of it as an area, this is measured in meters. That might be measured in meters. The area in the curve would be meters, meters squared. So this integral a to b f of x ds will give us meters squared. But we multiplied it by 1 over the width here. So we basically effectively divided by 1 of the meters, leaving us with just the unit of meters, which is distance. So it is really the average value of here to here, which gave us this. Just try so you don't get confused with the dimensions being off or something like that. So we use this formula, which I kind of gave you. It felt kind of magical. Don't worry about it. We'll actually cover it in more detail later. And we used our calculator to find this integral. And by using our calculator, it shows that this is how a calculator can approximate an integral or an area under the curve by using Riemann sums. Riemann sums being just little boxes and adding them all up. We then found that, we divided it appropriately, and it gave us an answer. So this may not actually be considered a Riemann sum problem, but I consider it as such because that's how the calculator does approximation. It probably doesn't actually do exactly Riemann sums. It probably does something a little bit more fancy like trapezoids instead of squares, or rectangles, but it's the exact same concept, exact same idea. Geometric shapes, finding the area. So this is the background that you'll use for Riemann sums, which then kind of becomes the intellectual foundation for integrals in general. And the nice thing about Riemann sums is not necessarily the for derivatives, we always go back to the original formula for a derivative or definition for a derivative. That's not really going to be the case here. The real value of Riemann sums comes with calibrating your spider senses correctly. The rules and properties of integrals, of how you adjust and add, multiply, and divide integrals, all comes back to area under the curve. And if you can think of things in terms of just boxes under the curve, you'll have all the same rule sets and it'll make it intuitively smoother for you. Thank you much. I will see you guys on the next one when we start formally discussing integrals and their properties. Thank you.